Okay, let's do some more solving. So ideally between the last video and this one, or at least in one way or another before this one, you've gotten some practice. That way we can kind of go through these in terms of the identity issues and the quadratic issues, and kind of under the presumption that your solving is at a reasonable place. Do make sure you're getting that practice. This stuff does take a fair amount of practice, as I said before. But in terms of using identities to help solve equations, it's kind of going to be like verifying identities was, in terms of not knowing necessarily what the right thing to do is to make the problem easier to solve. Just trying different things, looking and seeing what you can do, and seeing what helps. For example, looking at this problem, we might see sine squared and think, hey, we can make that equal 1 minus cosine squared x if we wanted to. It would still be plus sine 2x plus cosine squared x equals 0. But that might be helpful. It might not be helpful, but it's certainly something we could do. Similarly, this cosine squared x, seeing a squared trig function, that should bring the Pythagorean identities to mind. So that, might be helpful. It might not. Doing one of those but not the other might be nice. Who knows? We do notice we have a sine and a sine squared. That's generally going to make us think of quadratics. We'll talk about that when we get to quadratics. Having a trig function and its square in the same problem often should make us think about quadratics. But notice the arguments are different. This one's 2x and that one's just x. So the quadratic type logic isn't going to work real well. But hey, we could get rid of that 2x by thinking about our double angle formula and replace this with 2 sine x cosine x. You remember your double angle formula for sine, and that might be helpful. It might not be helpful. It doesn't set up any nice... Well, there's some factoring going on, but maybe that's helpful, maybe it's not. We could do any of those manipulations or none of those manipulations. It's just about seeing what you can do and kind of trying stuff. But looking at this problem, the thing that stands out to me is having both sine squared and cosine squared. If we rewrite this order, remember they're added together, so commutative and associative property, we can add them in any order. If we look at them this way, you can remember that sine squared plus cosine squared is equal to 1. That gets rid of all that troublesome other big squared trig functions and gives us a nicer thing that we can solve. We could still turn this sine 2x into 2 sine x cosine x, but as we said before, this is a nice, single trig function, and we want single trig functions for our solving if we can get them. So I'm going to keep that and just isolate it. Then we can throw in our nice inverse function. That's going to leave us that 2x as long as we're careful. And sine inverse of -1 is negative pi over 2. But again, we have to be careful. This sine inverse thing only undoes itself within our proper restrictions. We have to respect that by remembering to add our coterminals. Even though we only want answers within one rotation, this compression factor is going to change where our rotations are, or how big our rotations are. Now normally this would break into 2 sets, but because this is quadrennial, because the negative pi over 2 is on an axis, it's only going to give us 1 set, so that's nice. So to finish our solving, divide by the 2, and we'll get negative pi over 4 plus pi k as our general solution. Now we were asked for only solutions within the first rotation from 0 to pi, so we can start throwing in k's and seeing what's going to happen. If k is equal to 0, our theta would be, well, pi times 0 is 0, so it would be negative pi over 4. And negative pi over 4 is not within that restriction. Okay. K equals 1, negative pi over 4 plus pi, so negative pi over 4 plus 1 pi is going to give us 3 pi over 4. And hey, that's within our restriction, so that's a solution. Great. If we let k equals 2, we're going to add pi times 2, so we're going to add 2 pi, which would be 8 pi over 4. And that would be 7 pi over 4. Hey, 7 pi over 4 is also within our restrictions, barely, but it's in there, so that's fun. And then if we let k equal 3, we're going to be adding 3 pi, and that's going to get us past 2 pi, so that's going to be too big. So, hey, we got a couple of solutions. So 3 pi over 4 and 7 pi over 4. Great. That's your solution set. So recognizing that Pythagorean identity in there was certainly helpful. The double angle formula was in there, but wasn't helpful, so we didn't use it. So it's just about kind of trying things, seeing what you can do manipulation-wise that's going to be helpful for that problem. Now, one of the things that's going to happen a fair amount is that we're going to end up in situations where, we might think Pythagorean identity, and reasonably so, because this is a squared trigonometric function. But because we have cosine squared and cosine, dealing with this as if it was a, just a quadratic in terms of x or u or something else, is going to be handy. So if we, instead of looking at this as a, trig function, if we just looked at this as 2 times something squared plus that same something equals 0, if we look at the solving techniques we would use for something like that, we can apply those same techniques to the trig version. So, like, what would you do to solve the 2u squared plus u equals 0? Well, ideally, you would factor out a u. Get that equal to 0. And then the zero product principle says you have a solution when u equals 0, and when 2u plus 1 equals 0. So you'd have u equals 0 as a solution. And 2u equals negative 1, divide the 2, u equals negative 1/2 as your other solution. So that same solving technique, that same kind of way of factoring, will work if the objects in question are trig functions. They do have to be the same trig function, because they do have to be the same argument or same object that we're using our factoring tools on. So they have to be the same trig function with the same arguments. But as long as they are, we can do this. And frankly, even if it wasn't cosine squared, if this said 2 sine squared theta plus cosine theta equals 0, we'd be like, well, darn it, wouldn't it be nice if those were both cosine? Well, remember your Pythagorean identity. You can always turn a cosine squared into a sine squared. You'd have more work to do. You got to distribute this 2, and it becomes a bigger thing to factor. But you can always change sine squareds into cosine squareds and cosine squareds into sine squareds. So keep that in mind if you ever have this structure, but the functions don't match. But since they do match here, we're just going to use that same factoring tool. Cosine of theta times 2 cosine theta plus 1 equals 0. As long as a product equals 0, we can use the zero product principle. So we get cosine theta equals 0, and 2 times cosine theta plus 1 equals 0. Same things we got over here. And frankly, we can just go right to this is cosine theta equals negative 1/2. Let's do that. Cosine theta equals negative 1, divide by the 2, cosine theta equals negative 1/2. The difference is here we're not done. We still have to finish solving for theta. So we have to ask ourselves, what's the cosine inverse of 0? Well, cosine is 0 at, what's cosine 0? It's cosine 0 at pi over 2 and anything coterminal. It's also 0 at 3 pi over 2 and anything coterminal. So, yeah, so that's our general solution. We will have to bring that solution down. And, within our restriction, it's fairly easy. Within our restriction, we'll get pi over 2 and 3 pi over 2 for this side. But we also have to get our solutions for when the cosine is equal to negative 1/2, because that makes this a 0, which will make the product 0. So, but, again, the steps are the same. They're just kind of longer problems because we not only have to solve with our quadratic logic, but then we have to take those solutions and use our trig solving on them. So we'll get theta equals the cosine inverse of negative 1/2. Draw that out. Cosine's negative over here. Look at your unit circle. So at pi over 3, we get a negative 1/2. We also know there's going to be an answer down here in quadrant 3, because that's the other quadrant outside of our restrictions where cosine is negative. So that's going to be at 4 pi over 3. So we're going to get one answer at pi over 3 plus anything coterminal. And then 4 pi over 3 plus anything coterminal. But again, with no compression factors and no phase shifts, the only answers within our first rotation are going to be those two. Because if we add 2 pi, we're going to be too big. If we subtract 2 pi, we're going to be too small. So our other solutions are happening at pi over 3 and 4 pi over 3. You can check that for yourself by putting in different values for k if you'd like. So we really are just doing essentially two types of problems that we know. We know how to solve quadratics. We know how to solve trigonometric equations, or we're learning how to solve trigonometric equations. We're just putting those skills together. And that can take some practice, and you'll get a chance to get some of that practice. Let's see. Similar type of problem. The big thing we notice, we've got a trig function and the same trig function with the same argument that's being squared. So it should make us think of our quadratic tools. Seeing the sine squared should also, should still make us think about our Pythagorean identities. And again, that might be handy if this was a cosine squared instead. But changing this to 1 minus cosine squared beta when this is a sine beta really wouldn't go anywhere solving-wise. So handling it as a quadratic is going to be the best way. And it can be really helpful to rewrite this with those u's like I did before. Be formal here. Let u equal sine beta. Then this is 2u squared minus 5u plus 3 equals 0. because this is, how you're used to thinking about handling quadratics or factoring or those types of things. So looking at it this way might help, and frankly tends to. Ideally, this is factorable. If it's not factorable, we really can throw it in the quadratic formula. Quadratic formula would generate two answers. If those answers are real, then set sign equal to both of those answers, and we, proceed with the problem. But ideally, it's factorable. Let's see. We'd have 2u and u, and then I would need a 6, so it's got to be a 3 and a 1. That would be a -6 and a +1. Oh, that's not going to work. No, it isn't going to work. So maybe that's a 3 and that's a 1, and then a -2 and a -3 to make the -5. Okay, that'll work. So we get a u equals 3/2 and a u equals 1. Well, we could do that same thing here. We could say, okay, that's got to be 2 sine beta -3 and sine beta -1 equals 0, and then do the solving again. But we've really already done that part. And since u is equal to sine beta, we can just go back to these two solutions and say, hey, that's sine beta, that's what the u is, has to be 3/2, and solve that. And then the sine beta equals 1, and solve that. So really, consider using this u substitution to kind of use the visual cues that you're used to using to try to make the problems a little bit nicer. Now, the nice thing here, that sine beta equal to 3/2, ideally you look at that and go, nope, not going to happen. Because the sine has to be between -1 and +1, and 3/2 is bigger than 1. So that can't happen, so it's not going to generate any solutions. So the only solutions are going to come from this factor. It's nice when that happens. It throws us off. It makes us a little unsure of ourselves, but it's nice because then we don't have to do any more work for that part. Sine beta equals 1, so we're going to use our normal solving technique. Think a little sine inverse, and we're going to get beta equals, well, where does sine equal 1? Well, sine equals 1 at pi/2 in anything coterminal. And that's the only place it equals 1. It equals 1 at pi/2, and anything coterminal with pi/2, but there's nothing in these other quadrants. And again, that's because it's on the line. It didn't happen with cosine because it was looking at cosine of 0. But we do need to be careful about that. So, and I like to think about it as, if we had an answer over here, we'd have an answer over here, and those answers are essentially just coming together and landing on top of each other, giving us one common solution, if that's helpful. If it's not helpful, feel free to ignore it. But that's going to be where all our general solutions are coming from. We're only asked for an answer between 0 and 2 pi. So again, with no compression factor or phase shift, we're just adding and subtracting 2 pi. So this is within our first rotation, and adding or subtracting any amount of 2 pi is going to get us out of the first rotation. So that's our only answer. The big thing tends to be recognizing that we have to handle this as a quadratic. As soon as you recognize, oh, it's a quadratic of this structure, so then you can confidently use your quadratic tools and then get those two tend to be smaller trig problems, and then handle those trig problems hopefully confidently once you get some practice. Tends to work out nicely. Now, this sounds a little worse because the language they're using. But determine the inputs for which the graph of this thing, why is that still? Sorry. Why is it still doing that? Hold on, let me fix this. Alright, sorry, I'm not sure what that was, but I think I got it fixed. Yeah, okay. So, determine all inputs for which the graph of this function intersects the graph of that function. Well, we could, work at drawing that out. Sine of x equals the graph of cotangent. We have to remember what cotangent looks like. So we're trying to find all these intersection points, and I don't know, how good that drawing is, but we're trying to find a bunch of those intersection points. How we're going to go about that is probably a lot simpler than this sounds. If we want the graph of this to equal the graph of the other one, then all we have to do is, so that's all we're going to do. We're going to let the sine of x equal the cotangent of x and try to manipulate this as much as we need to solve it. And we'll get all of those solutions as long as we're careful about our general solution logic. So, how do we want to approach this? Well, I don't like cotangents, so my first inclination would be to change that to 1 over the tangent of x, because I don't like cotangents. Well, I also don't like denominators, so how about we multiply both sides by tangent of x? Is that going to be helpful? I don't know. I'm just trying stuff. So those are going to cancel, equals 1. And I'm going to write this as sine x times tangent x equals 1. Okay, that could be handy, but I'd like to have one trig function as opposed to two. Well, we do know that tangent is sine x over cosine x times sine x equals 1. So that's sine squared x over cosine x equals 1. So that might be helpful. I'm back to having a fraction, though. Let's stop it being a fraction. Let's multiply both sides by cosine x, so it stops having fractions in it. So I got sine squared x equals cosine x. Well, I've got a squared function and a non-squared function with the same argument, so that's not bad, but it would be nice if they were both cosine. So how about a little Pythagorean identity in there, that sine squared is 1 minus cosine squared x equals cosine x. Well, now I've got, what kind of looks like it could be a quadratic. I got a squared and a not squared. I kind of like it set equal to 0, but it's kind of like, at this point, do I want to go off and think of it as 1 minus u squared equals u? Or do I want to keep with the cosine functions? It's really up to you. Either way, if we add u squared to both sides, we get u squared plus u equals 1, and then subtract the 1 from both sides. 0 equals u squared plus u minus 1. So the same manipulations over here would get us a cosine squared x plus cosine x minus 1 equals 0. Just be adding that over, subtracting that over, or however you want to manipulate it. And then ideally trying to factor that, but I don't know, this doesn't look factorable. We'd have u and 1 and 1, and there's no way to get that nice one in the middle. Gosh, I'd hate to use quadratic formula on this, but if that's what it takes, so then u would equal what, -1 plus or minus the square root of 1 minus 4 times 1 times -1 all over 2. That's ugly. So u equals -1 plus or minus the square root of 5 over 2. Ugh. That's ugly. That would leave us with cosine x equals -1 plus the square root of 5 over 2, which we'd have to solve approximately. And cosine x equals -1 minus the square root of 5 over 2, which we'd have to solve numerically. By numerically, I mean you would have to get a decimal approximation for that cosine inverse, unless we make the observation that this is certainly going to be bigger than more negative than -1, because that's going to be, square root of 5 is a little more than 2, so -1 minus something a little more than 2 divided by 2 is going to be bigger than 1, so that's not going to make a solution. Here, though, that's a little bigger than 2, so that's going to be a little bigger than 1. So yeah, that looks like that might generate a solution. Before we dig into that, let me make sure I haven't done anything funny here, or there wasn't a better way to go about this. So let's look at this for a second. Nope, that all looks fairly reasonable. Sorry about that. That all looks fairly reasonable. It's just going to be ugly, but, ugly's okay. So you could get a decimal approximation for the -1 plus the square root of 5 over 2 if you wanted to, but we're going to have to use this in technology anyway, so we might as well just have x as whatever the cosine inverse of -1 plus the square root of 5 over 2 is. But don't forget and plus rotations. But we're also going to need the secondary answer, so we might as well turn that into a value. So the cosine inverse of -1 plus the square root of 5 over 2, if you grab your calculator, is going to give you a 0.905-ish. So that plus 2 pi k. Now again, that's an angle, remember. So that angle is, this is a positive number. The square root of 5 is bigger than 1, so it's a positive number at an angle of 0.905. So it's in quadrant 1. The other angle, because it's cosine, that other angle has to be in the other quadrant in which cosine is positive, so that's got to be down here with the same reference angle. So we really could, anchor the other one just at -0.905 plus 2 pi k. These are both for k and integer. Or if you wanted to, calculate that angle, the positively oriented angle, which a lot of people prefer to do, then take 2 pi and subtract that 0.905 to figure out what that big angle is. And it's about 5.379. 5.379 if you perform that subtraction. So you could have this value be that 5.379 as well if you wanted to. So that's going to be our two sets of solutions. And that's going to be all of the places that those two graphs intersect. And, of course it's a lot of values. It's all of these little intersection points over and over and over again. And, in some ways I think it's nice to see that, hey, we can use the quadratic formula if that's what we have to. It's, nice when these are factorable, but they're not, a lot of quadratics, most quadratics aren't factorable. And that's okay. If it's not factorable, you just get what you get from the quadratic formula. If this had a negative in the square root, if it was non-real, then we just wouldn't get any solutions at all. It was nice to observe that this is bigger than, or more negative than -1. It's outside of the range. But if you hadn't noticed that, and as soon as you've tried to find what the cosine inverse of -1 minus the square root of 5 over 2 is, your computer or calculator would have said error. There isn't an answer to that because that's outside of the range. So, it's nice to see an example where we had to use, the big gun of quadratic formula. But it does make them seem a little icky and does make you nervous, but, check back. If everything looks right, then go for it. And if it helps, we can always check. Put 0.905 in for sine x and in for cotangent x and see if they're equal. About. Should be approximately equal because that's an approximate value. So, we can always check. This is our last example, isn't it? So that was kind of a hairy one. I'll give you that. And a lot of this manipulation took a fair amount of being confident about it. And even trying to be confident about it, I lost a little bit of confidence a couple times there. But just, that's why I say don't try to worry so much about what you're supposed to do. Just play around with what you can do and, wait for something to fall out. Okay, here, well, I do have a, double angle formula here. They are both sine, which is nice, but the fact that that's a theta and that's a 2 theta is a problem. So I might be tempted to at least look at what the double angle formula would tell me for that. Equals 3 sine theta. Now you might be tempted to divide both sides by sine theta and have it cancel out, but be careful. You can't do that. The same way as, if you had, say, 2u squared, I know that's not what we have here, but 2u squared equals 3u. You can't divide both sides by u and have that cancel because u might be 0. So if u was equal to 0, that wouldn't be legal. We don't know it's legal, so we can't do it. So what we would up here do instead, shouldn't have scribbled that out. What we would do instead is subtract it over set equal to 0 and then factor. So that's the same thing I'm going to try to do here. It's a little uncomfortable to have cosine here. It'd be nice if everything was just sine, but notice if we have that set equal to 0 and we factor out the sine theta, then we're left with a sine argument and a cosine argument that are now separated and equal to 0, separated as factors and equal to 0. So we can separate those. So we get sine theta equals 0 by zero product principle, or 2 cosine theta minus 3 equals 0, which would mean 2 cosine theta equals 3, so cosine theta equals 3 halves, and since that's bigger than 1, that can't happen. I'm not going to generate any solutions. So that's nice, that side's done. We did say we had to be careful about sine being 0. We can't divide because sine might be 0, and hey, sine is 0, so I'm glad we were careful about that. But this is going to generate solutions because sine can equal 0, so sine inverse both of those, and we'll get theta equals sine is equal to 0 at, 0 and anything coterminal. It's also equal to 0 at pi and anything coterminal. We were asked for answers in the first rotation, and again, the lack of phase shift or compression factor means we're just going to have those two solutions, 0 and pi. It doesn't always happen, but it is fairly common when you use factoring on these for one of the terms to generate solutions and the other one not to. It's possible neither of them will generate solutions. It's possible both of them will generate solutions. So don't be surprised if at least one of them it just can't happen like it did in several of our examples. It's really not unusual. It's more unusual for neither of them to cause solutions. But that does happen sometimes. Um, we just kind of want to be careful about that and aware of that. So just like with the other solvings, make sure you're getting plenty of practice with these. They do take a fair amount of practice. Let your instructor know if you have questions on the ones from the homeworks and whatnot. These can be challenging. Make sure you're putting that time in. And have a wonderful day.